Hello. We've now introduced some basic ideas about probability, and we're about to start building on those ideas today. In particular, we're going to look at how computational systems are so very convenient for modeling behaviors of noisy or uncertain systems, especially in estimating the values of parameters of those systems. Before we start, it's worth noting that the history of probability is intimately connected to the history of gambling. It is the existence of uncertainty that makes gambling possible, and the existence of gambling provoked the development of much of the mathematics needed to reason about uncertainty. So I guess it's a good thing that people were willing to lose their money. Contributions to the foundations of probability theory by Cardano, Pascal, Fermat, Bernoulli, De Moivre, and Laplace, among others, were all motivated by a desire to better understand and profit from games of chance. Most of the early theory revolved around games using dice. Reputedly, Pascal's interest in the field began when a friend asked him the following question: would it be profitable, given 24 rolls of a pair of dice, to bet against there being at least one double six? You'll recall there's 1 6 on each six-sided die. Amazingly, this was considered a hard problem in the mid-17th century. Pascal and Fermat, two pretty smart guys by the way, exchanged a number of letters about how to resolve this issue. Of course, to us, it should now seem like a very easy question. On the first roll, the probability of rolling a 6 on each die is 1/6. So the probability of rolling a 6 on both die is 1/6 squared, which we know equals 1/36. Therefore, the probability of not rolling a double 6 on the first die is 35 over 36 squared. If we look at 24 rolls, we have to look at 35 over 36 to the 24th. So what value is that? Well, let's go over to our Python window and check it out. We can look at it in idle here and say that it should be 35.0 over 36.0 to the 24th. Ooh, it's very close. So you can see why Pascal's friend really didn't feel he could answer this experimentally, that it required some analysis to see what the answer is. But as it is, you can see that it's just not quite there. Not quite a half. Okay, that's what the math says. I'm a skeptic, and I wrote some code to check Pascal's math. I know, who am I to think that I should question the great Pascal? What the heck, it's my course. All right, so we have roll die, which we've looked at before, and then we're going to check Pascal. We're going to pass in number of trials, that will be an integer, and roll, which will be a function. In a little bit, we'll see why. We'll start with yes equals 0. For I in the range number of trials, for j in the range 24, we'll roll the first die, we'll roll the second die. If they both come up 6, we'll set yes to 1, and then we'll break. And when we're done, we'll print the probability of losing equals 1 minus yes over the number of trials. Let's give it a shot. We'll call check Pascal, 10,000 trials, and we'll pass in the function roll die, defined up here, that gives us a fair die. Pretty darn close to what Pascal computed, and probably if I'd done more than 10,000 trials, it would have been even closer. Now we have to remember that both Pascal's math and my simulation only hold under the assumption that each die is fair, i.e. the outcome of a roll is truly random and each of the 6 outcomes is equally probable. That's not always to be taken for granted. The pair of dice pictured on this slide were excavated from Pompeii, and you can see that one of them has been opened up, and that's because there was a little weight inside there to make sure that when it was rolled, in fact, it was not equally probable that each side would end up down. More often than it should have, the slightly heavier side would end up down. All right, let's, just for fun, build some cheating dies ourselves. So I'm going to replace roll die with this other function, roll loaded die. It starts by saying if random.random, and you'll recall that returns a random value in the range 0 to 1, is less than 1 over 5.5, I'm going to return 6. Now, if I wanted the die to be fair, I would have made this 6, but I don't. I want 6 to come up just a tad more often than it really should, and then the other 5 numbers are equally probable. Not a big difference, but let's see what it does to the outcome. And now you can see why I made roll a function rather than building it in to the Czech Pascal simulation. So we see here, well, I got a slightly different answer this time when I ran the simulation with the fair die, 0.5131, but a really big difference when I put in the cheating die. Notice the probability has dropped dramatically. So there are 2 morals from this story. The first, don't play a game of dice with somebody who brings their own dice to the game, unless you know them very well or you don't care whether you win. More importantly is the moral that simulation is a wonderful tool for exploring what-if questions. I asked the question, what if I made the die just a little bit unfair, so much that no one would notice it? Would it change dramatically the probability of winning or losing the bet? And we saw that it would. That's one of the reasons people love simulations, is they can explore these kinds of questions. The simulation we just looked at, like many of the other simulations we've played with, is an example of something called a Monte Carlo simulation. The term Monte Carlo simulation was coined in 1949 by Stanislaw Ulam and Nicholas Metropolis, 2 very well-known 20th century mathematicians, in homage to the game of chance played in the casino in the Principality of Monaco, pictured here. Ulam, who is best known for designing the hydrogen bomb with Edward Teller, invented the Monte Carlo method in 1946, even though he didn't name it until 49. Here's his own description of how he invented it. The first thoughts and attempts I made to practice the Monte Carlo method were suggested by a question which occurred to me in 1946 as I was convalescing from an illness and playing solitaire. He probably was not playing it on a computer, by the way. The question was, what are the chances that a Canfield solitaire laid out with 52 cards will come out successfully? After spending a lot of time trying to estimate them by pure combinatorial calculations, I wondered whether a more practical method than abstract thinking, oh, I hate that abstract thinking, might not be to lay out, say, 100 times and simply observe and count the number of successful plays. This was already possible to envision with the beginning of the new era of fast computers, and I immediately thought, as I'm sure all of you would, of problems of neutron diffusion and other questions of mathematical physics. Later, in 1946, I described the idea to John von Neumann, and we began to plan actual calculations. Of course, the fast computer is a relative term. Ulam was probably referring to the ENIAC, pictured here. It could perform a grand total of 10 to the third additions per second. And by the way, it weighed about 10 to the ninth tons. It was really big, as you can see here. Just for perspective, today's computers perform about 10 to the ninth additions per second and weigh, I don't know, something like 10 to the minus 3 tons maybe. The first known use of Monte Carlo simulation on a practical problem was in the Manhattan Project during World War II. It was used to predict what would happen during a nuclear fission reaction, something that they had been unable to solve mathematically and were enormously pleased that they had found an alternative approach. But really, Monte Carlo simulation didn't take off until the 50s, when computers became both more common and more powerful. A Monte Carlo simulation is a method of estimating the value of an unknown quantity using the principles of inferential statistics. The key words here are estimating. We will not typically be able to get exactly the right answer using a Monte Carlo simulation. And inferential. We're inferring something. I'm not going to go into the mathematics of all of this. It's rather complicated, and I would certainly get it wrong. But the intuition is really quite simple. The intuition is that a random sample tends to exhibit the same properties as the population from which it is drawn. So, for example, if I randomly sample the people in this course, say I sample 1,000 of them, and 54% turn out to be female, and the other, I guess it should be 46% turn out to be male. We probably have no hermaphrodites. I'm going to assume that that ratio is representative not just of the 1,000 people I sampled, but of everybody taking the course. As we'll see later, this is valid only if I take enough samples and my samples are truly random, which makes them representative of the entire population. We can see this a little bit more easily if we think about flipping coins. Suppose Harvey Dent flipped a coin and it came up heads. You would not infer from this that the next flip would be heads. But suppose he flipped it twice and it came up heads both times. You might reason that the probability of this happening for a fair coin, i.e. a coin where heads and tails are equally likely, was 1/4. So even with 2 in a row, you're not going to conclude that the coin isn't fair. But suppose he flipped it 100 times and they all came up heads. At that point, you might feel safe in inferring that the coin has a head on both sides, i.e. it is a 2-headed coin. Whereas this is an Australian coin. Who knew? Your belief in whether the coin is fair or not is based on the intuition that the behavior of a sample of 100 flips is similar to the behavior of the population of all flips of the coin. This belief seems pretty sound when all 100 flips are heads. It just seems highly unlikely that that would happen by accident. After all, if the coin were fair, the probability of getting 100 heads in a row would be 1/2 to the 100. Pretty darn unlikely. Suppose, on the other hand, you flipped it and you got 52 heads and 48 tails. Well, you could feel safe predicting that there are both heads and tails on the coin, but would you really want to predict that this would be the ratio you'd see if you did another 100 flips? Or for that matter, how good would you feel about even predicting that you'd get more heads than tails? I wouldn't feel very good. Let's look at a simulation that shows us why you shouldn't either. The function flip is intended to flip a fair coin none-flip times and return the fraction of flips that come up heads. For each flip, random.random returns a random floating point number between 0 and 1. The midpoint of this number, 0.5, is arbitrarily assigned the value tails. However, given the vast number of floating point values between 0 and 1, it's highly unlikely that this will affect the result. I then accumulate the number of heads and return the number of heads divided by the number of flips, thereby giving me the ratio of heads to tails, because every flip that's not a head must be a tails. Let's see what happens when we run it. For I in range 5, so that will be the number of trials, we're going to call flip, well, let's do a small one first. Let's call flip with 10 coins and see what we get. 6, 5, 4, 7, 6. Well, not much of a trend there. Let's just try it again for fun. We should get different numbers. 7, 4, 7, 4, and a 3. Very low ratio. So if we look at this and we see that we've got numbers that seem kind of all over the place, it seems that it would be inappropriate to assume much, other than maybe that the coin has both heads and tails, from any one trial of 10 flips. That's why, by the way, we needed to do multiple trials. Because otherwise, if we just ran one and we came out with the number, we might get fooled into believing it. Well, let's see what happens if instead of 10 flips, I do 1,000,000 flips. 1,000,000 per trial. Well, the numbers are all different, but not very different. So notice how much tighter this distribution is than the distribution we had either of the previous times we ran it. So intuitively, we can feel much better about this experiment and, in fact, come away convinced probably that the coin really is fair. In the next segment, we'll talk about why our intuition that this really is the right answer is actually justified.